I am here to discuss with you about the influence line diagrams of structural analysis. We will spend 3 days and 5 hours in discussing the materials, and we will have 1 hour straightway at last for the discussion. Influence line diagrams, let us discuss from very beginning that what is there in our disposal. We have the textbooks, we have many web resources. So, where from to grasp the material, and before that I will give you some introduction about the shear force and the bending moment diagrams and the sign conventions itself. Now, let us talk about the textbooks which are available in market. So, in IIT Kharagpur we follow the structural analysis book of Professor R.C. Hibbeler. So, it is of Pearson Education. That is this book we follow, and here are the contents. So, many of you might have seen this book, and sometimes we are assisted by many reference books. One of them is of indeterminate structure analysis by C.K. Wang, and sometimes it will be convenient to actually see the book of Professor Menon of IIT Madras, which is a structural analysis. I also have prepared the class note following Professor A.K. Jain's book, both of IIT Roorkee. So, this 2 volumes also assisted me a lot because of its content, and there is the second volume of Professor Jain, and there are many books actually. And one typical book I will show you for it is a curious finding that in our theoretical and experimental endeavors, that most of the books, and they are quite voluminous, they discuss about the experimental, they discuss about the analytical approaches while dealing with the influence line, which is mainly meant for actually the practicing engineers who are going to build something. So, how can you avoid the experimental or direct observational part? I have got one book which of Professor Vaidyanathan and Professor Perumal. It is an old version. So, I am yet to get any new version. So, this book of Professor Perumal and others, this discusses something about the experimental approach for the influence line diagrams. So, let us now start our journey. So, we will have in our disposal 5 hours of PPT, along with many a times I will write on the board, and you can see that. Also, in between I will show you the class notes or some problems from the books and discuss mainly the solutions of this problem. So, before starting the topic, let me tell you that my observation that influence line diagram is not that highlighted among the students. It's backseated as compared to many of the other important topics. All are important for our journey to understand the structural analysis and the behavior. The thing is that 2 things are very important. One is the sign convention used in many of the books. So, it is sometimes the sign conventions are arbitrary. So, it is correct in either way, but you have to follow only one and do not confuse with the others. You have to have a clear idea about what sign convention is followed in different books. You need to fix up your sign convention in which you will be discussing your materials, but you need to understand other people's sign convention as well, so that you can refer to the reference books, interpret the results given there, and also correctly draw your figure correspondingly. This is very important. Another thing which I find that what is the main reasons that influence line diagrams are sometimes not well read by students and also not well understood by the students, that the voluminous nature of the textbooks, where hundreds of pages are discussed mainly on the case studies and in detail about the trusses and beams with different load configurations. So, the treatment is mostly not concise in many of the textbooks. That may be a repelling factor for learning this topic. So, in our approach we will be very concise. We will learn only the basics, leaving the rest of the detailing parts to the students. Once the student understands the basic, it will be easier for him to actually understand the rest of the things, and we'll leave it to that. Actually, the books are reference books and mean for even practicing engineers, and which from which they can learn their practical problems. And of course, we are blessed that there are experimental techniques in this influence line, drawing the influence line diagram. Influence line diagram can be actually drawn analytically. It can be determined experimentally as well. So, now the theory versus experiment, there is always a conflict with the students, that, and most of the time the students are shy away from the experimental observations because of the difficulty in conducting an experiment. It is not possible in this coursework and today's presentation to go in detail for the, I have not included that also, but I understand that for your complete learning, once this course is completed, you will explore the experimental approaches as well. I will show you the how to approach to that. So, with that, let us begin, but before we directly talk about the influence line diagram, let me clear the doubts about the sign conventions which are followed for the bending moment and shear force. Why especially bending moment and shear force? Because we are civil engineers, so that is why we will be mainly dealing with structures which may be slender, and if a slender structure is laterally loaded, our main load is gravity load, and even the live loads are also vertically downwards. Due to that, a transverse slender member is going to be subjected into mainly the predominantly the bending moment and the shear forces. So, for the beam type of structures, both predominate. So, we have the other effects like the axial forces, especially applicable for the trusses as well, and torsional things also are there, but the bending moment shear forces actually require much more and actually definitive attention from the students. So, let me clear what can be the sign conventions, the doubts regarding the sign convention. After that, we will move to the PPTs and discuss about the influence line diagram, what they are, how to construct them, what is the use of that, we will discuss about them. Now, for that, I have, you can focus here, I have taken one here, one textbook. It is an old textbook, but it is very nicely explained there of Professor Crandall, Normal and Lardner. So, I will show you the, here are the names of the professors. So, you can later on see if you get an opportunity, but we will show you a diagram here. So, you see, when the stresses are three-dimensional in a body, so how to represent the state of stress here, we have one force, suppose this is a cuboid inside a body, and one is the normal force, another will be the shearing force, which will have two components here. So, you have the sigma xx as tau xy and tau xz. The x means it's the initial notation, you can say that is the actually that these are the shear force stresses and these are the normal stresses. Now, if you see that if the same structure being a 3D, if it now becomes slender, this is one of the pages, if it becomes now slender, you see now the stresses, you can see, you can focus it there. So, here are the normal forces and here are the two shearing forces. The moments about this axis, moment about this axis, moment about this axis are shown. This is how a slender member in its cross section are subjected to different stress resultants. So, you can easily find out that this is the moment here which will bend the structure in x y plane, which will bend the structure in x y plane, and this is a shear force which is going upward direction as because we have oriented our x, y and z axis in this way. That is why it is the positive direction of the axis which is also trying to push it up the section, and that's the shearing force. The other things are off the plane quantities, and this will at this moment will twist the section, and we will refrain from discussing them. Now, coming to the shear force and the bending moment diagrams, when you actually draw them, let us see the same book, actually we can focus here. You are familiar with the shear force and the bending moment diagram. You see that this force is creating a reaction here and here. So, this reaction, if I consider a section at certain distance, this force will create a moment about the axis perpendicular to the plane of the paper, and also it will try to shear off. So, depending upon the material and its behavior, it will be subjected to shearing force and the bending moment at this section. Now, we represent the variation of this shear force and the bending moment in space. The spatial variation of the shear force and the bending moment are represented through bending moment diagrams and shear force diagrams. So, the bending moment is the force multiplied by the distance, and the shear force is just the force itself, and we represent them as the shear force and the bending moment diagrams, and we have to follow certain sign convention to draw them. Here in this book, it is drawn as this, following this sign convention, where if you take an element, if it is left down and right up is taken as positive, and this moment, which is a sagging moment which can hold water if it can bend the structure at its top, that is a positive sign convention for the bending moment. So, you can easily imagine in this sign convention, the shear force created by this force, this reactive force, is always negative as per this sign convention. It is drawn as negative shear below the line. Similarly, this force which is creating the right part up, it is drawn as this, that it is a positive shear force, and this is the bending moment. Probably this is it is actually consistent with the figure we have shown earlier, but you see that it's most of, in our cases, if I show my sign convention, most of our cases are exactly we have to follow one of the sign convention. There is no question of being correct. It is the consistency which I feel the earlier book I have shown is maybe more appropriate, but there is no harm in sticking to other sign conventions. In fact, the books exactly do that, and the sign convention I follow and many of the books follow. In fact, the textbook followed in IIT Kharagpur, the R.C. Hibbeler's book, they follow the opposite sign convention. That means, left up right down is positive shear, which makes the element like this, and this is considered as a positive shear, and the bending moment is the same as previous. So, for us in this discussion, we will stick to only one sign convention, which is the left up right down for shear is positive and the sagging bending moment is positive, and with that we will discuss everything. So, you can imagine that if the same diagram, I have shown you this diagram, if I draw for my purpose, if I draw it for my purpose, I will draw the same diagram here. I have a load here, so a reaction here and reaction here. So, my shear force diagram, according to my sign convention, it is left up right down is positive for the shear, and for the bending moment this. So, for me the same shear force diagram will be drawn like this, where it is left up is positive for me and right down is negative for me. So, it is right up. So, according to this is negative shear, and this is the middle line, and for the bending moment I have the same thing. There is no issue with that. Now, I am not putting the value. One thing is that in which direction I will plot the bending moment, that also it differs from books to books. So, this book and most of the books are drawing the bending moment diagram on the compression side of the beam. So, it is absolutely arbitrary. If I draw the diagram like this on the tension side, in fact, many of the civil engineers will prefer to draw it on the tension side, because he can immediately find out the locations of the reinforcements there. So, he needs to stitch the impending cracked portion. That is why it is more appropriate for civil engineers to draw on the tension side. But again, it is completely arbitrary, and that is why there is no point in actually sticking to either, and we follow it just arbitrarily. Okay. I think let me discuss with the students that perhaps you have understood. Yeah. So, before actually going to discuss about the influence line, I have spent quite some time about the sign conventions followed in different books and also the sign conventions we will follow in our discussion. So, left up, right down is positive shear and the bending moment is sagging bending moment is positive for us. So, this is the sagging bending moment is positive for us. So, with this sign convention I have to proceed, otherwise there will be tremendous confusion about the results I am showing to you. Once again, these are absolutely arbitrary. You are free to choose any sign convention. I will advise you that unless you are really conversant with the different sign conventions, follow only one. If still confused, follow one textbook. Do not see the other textbook immediately. Complete the topics from one textbook and you will understand it fully. Then after some time when you are conversant with the sign conventions, you will follow others as well. There is no mistake, it is just arbitrarily chosen. And one more thing I need to discuss, we will extend our understanding of the influence line diagrams from statically determinate structures to statically indeterminate structures. So, you need, I hope you have some knowledge about the static indeterminacy and static how to determine them. So, static indeterminacies are that we have more number of supports or more number of members than it is necessary for maintaining the static equilibrium and stability of the structure. So, if we have more than required, then it will be not possible to determine the reactions or the member forces within the body also from just exclusively from the static equilibrium conditions. You need the conditions of your displacements to determine the stress resultants or the reactions. So, I hope you are familiar with, just I will show you some formula which may strike to you if it can be found out from observation alone. In fact, it is better done with the observations, the what is statically indeterminate and indeterminate. What do we do? If you become to some extent expert in that, you will mentally remove one or two supports or the members to see that now if it looks determinate, and also to explore whether this is affected by the sinking of supports, the temperature changes, differential temperature within one or two members, or the lack of it. If it appears to be affecting, then probably it is not statically determinate. So, like that, but I will show you some formula which you need to you can just recapitulate, that you can use that r minus 3n to find out the indeterminacy in a beam, m plus r minus twice j for the trusses. So, now for the frames thrice m plus r minus 3j, and for the 3D trusses and the 3D frames are like this. You no need to remember, this formula. It can automatically come from, so I can keep it here, automatically come from your understanding of how many conditions are known and how many unknowns are there to be determined, and from there you can form the equations yourself. Anyway, we are all set to explore the influence line diagram. Before starting, let me I have shown you the textbooks where it is available. In fact, I have seen at least another 15 textbooks available in the market. They are extremely elaborate, and many of them spans the influence line diagram over 100 pages, and that is why I have shown you the books which are to some extent concise, but there are I am not saying that the other books are less useful. There are other books are very, suppose I have just extracted one example from Professor Ramabutham's book. So, there are lot many examples solved into those books, but first hand knowledge, first time it is to be acquired from a book which is very concise. After that you can switch to the elaborate books, and also the internet is full of web resources including ours. You have perhaps noticed that we have the influence line diagram module from IIT Kharagpur, and we have that your NPTEL coursework. So, I have all these four modules, and I can show you that this NPTEL course modules are here with me, and they are quite elaborate, and all this your discussion about the influence line goes like us. we are more concise. We have no time because these are background materials the student will study in his leisure. It is possible, but today we are interactive session. So, we will be very concise. So, let us start with we are fully ready for the show. So, let us start influence line diagram. Let us start day 1 session 1. Here it is a session summaries. We will come to this next. Yes. So, introduction to influence line. Structures are subjected to various kind of loads. Dead loads including the self weight of the structures are applied at different locations and do not vary in magnitude with time. You are familiar with. Live loads vary. I am not directly reading the slides. You can read in your leisure, and then I am just giving the essence of the slides, that live loads can vary in magnitude as well as their locations may be changed with time. So, how to deal with that? Sometimes in our treatment we treat uniformly distributed live loads, because to simplify the uniformly distributed live loads, to simplify the analysis, we account for the dynamic effect of the live load through impact factors or something, and also we take statistically the uncertainties into this loading and come up with a uniformly distributed load which will not be exceeded in by any means, and we can treat the live load similar in line with the dead load. Yes, next slide is this. The most appropriate method we are familiar with, that we express the stress resultants, the internal stress resultants, which are the bending moment, shear force, axial force, or the torsional moments. If we are focusing on bending moment and shear force here, and for the trusses the axial stresses, and also the external reactions. The most appropriate and most popular and accepted thing are the bending moment shear force diagrams, and the students are already familiar with that to draw the variations along the spatial variation along the span. Probably this is the reason he is already biased with such type of diagrams in space. It is mentally to some extent a barrier to accept the time variation. In case of live loads, whose magnitudes are concentrated at discrete positions and also changes location with time, too many such diagrams will be needed to express the variation, particularly considering the various time instants in which such loads will be applied. And then also the designer, mainly his interest is to know the variations at critical locations. So, he is exploring that what is the variation in different places, but if the structural form is known to him, he may actually be knowing where these variations become critical, and he will be interested to see the variation of the live load there. Probably his interest is to see that if the load changes positions, how the bending moment and shear force vary at a particular locations. To describe the variation more concisely, various position of live loads, such diagrams are represented at particular locations as the loads move over the structure following designated load paths from functional requirement. So, the designated load paths are actually you see that designated load path means for bridges, a railway bridge, a railway line is laid. Even for road bridges, the line is laid where the actually the heavy trucks will ply. Also in industrial cranes, where it is applied, you know where the load is hung and how it is moved. Also in building frames, how the live loads will be transferred to its girders, and from there to the columns is actually known to you. From functional requirement, the load paths are known to you. Although the locations of the loads at various time instants are recorded, the inertia forces are not considered. I have just explained to you that it is in terms of an equivalent static load, and our treatment is fully static. Now, come straightway to the introduction of influence line. The influence of the time varying loading on the external reactions, that is the reactive forces or moments, or on the internal stress resultants, that is the bending moments, etc., at selected locations of a structure can be designated as influence line diagram. Now, coming back to our discussion once again, usually you see we are exploring that what is the effect of the loads at critical locations. So, that is we define our maybe our influence line diagram. Now, what should we do? The loads will vary from in structures. So, let us form the this proposition in terms of a unit load, and if we deal with a linear structure, if we are interested about the response due to the loading and the linear, the Maxwell superposition theorem and others, that all these things are valid, then probably it will be judicious to form such diagrams in terms of a unit load, and later on do something so that for the effect of the actual loads will be very quickly determined. So, usually a single unit load is conveniently placed instantly. I say instantly just to give an equivalent static effect at various locations to quantitatively draw such diagrams, and the effects of the actual loading, both concentrated and distributed, single or multiple loads, can be determined using superposition principle. It is also possible to guess the qualitative shape of the influence line diagram. We will discuss using a principle which is called Muller-Breslau principle, which is a very, very powerful tool in structural analysis. You will see that. Now, once such diagrams are made available, it will be possible to tell at a glance where the moving load should be placed, to have the maximum effects influence. That is why the influence line diagram of the chosen stress resultants, as for example, bending moments at the selected point. The magnitude of the influence can also be assessed readily from the ordinate of the influence line diagram. And influence line diagrams are used in the design of bridges heavily. The bridge designers need to know, as the vehicle, suppose a train moves on a bridge in a particular locations, how the bending moment and shear force are changing, and that is its influence. And also the industrial crane rails, you have some kind of crane, and then you want to shift a heavy load from one to other positions. You need to know how the crane itself is subjected to various stress resultants. The conveyors, which takes distributed loads, that also how it is the moments and the shears are actually working there, or the tensile stresses into the conveyors, and the warehouses where a lot of materials are stacked, heavy materials, and frequently moved with forklifts type of thing, and follow a particular load path to reload and unload everything. So, those are the things where your influence line diagram will be extremely useful. So, now the difference. So, you understood that we are introducing some other diagrams. So, now coming back, now if this load is not static, but it moves from one position to the other, what will you do? You can do one thing. So, let me tell you what is life without influence line. So, you will place the loads at different locations, and then you can according to my sign convention. So, it is positive, yeah. So, here, and then the things will actually change, and we will have a bending moment diagram different. So, similarly for different locations, we will draw different bending moment diagram, we can plot them together and then try to find out that what is the profile, how it is changing. All these things need to happen before I understand what is the effect of the live load. Or else I can do, again still life without influence line, I can select a section, and there I can represent in diagrammatic form the variation of such quantities along a bar, that if you move a load, how at this section the reactions is changing. Again I can have another bar to indicate that if you move a load at this section, how this reaction is changing. So, now these are, this is how you need it to represent if we are not aware of the influence line. So, is it not better that what I do is that now I select a location where I am interested about to determine the variation, suppose the shear force, and then as the load moves over it, I plot along the length the influence line, along the length the variation of the shear forces. So, probably this will, so now this corresponds to this is the shear force diagram of the same beam with a constant position of the load, and this is the influence line diagram. I should have drawn it in the middle to comply. So, once again I am drawing it here. So, for you this is the shear force diagram. this is a positive and negative shear for the beam which is loaded in the middle, and then you have the suppose the influence line diagram for the shear force here, which is like this. So, now it is very difficult to digest, because what I am doing actually, I am sitting here, I am this is the shear force diagram is completed. Now, for the influence line diagram, I am sitting here and then observing how actually the shear force is changing there as the load moves on the space, So, what is there? If my load is here, I am sitting here, the shear force here is plotted actually with a unit force. When it moves, the shear force is actually indicated here. That means, I am always sitting here, So, this is probably the sources of confusion of the students. Shear force diagram is not a basic entity. It's sorry, not shear force, the influence line diagram is not a basic entity. We are just manipulating the representation of the shear force diagram in such a way that it incorporates the information of a moving varying load at a particular section we are drawing. And that is why, if you try to understand the shear force diagram along with the influence line diagram, if you draw the shear force diagram at a point and try to understand the influence line diagram at the same point for the same quantity, the diagram sometimes may look similar, but they have completely different interpretation, as I have just explained to you. I think you need to understand it properly, and we will gradually understand as we move. Yeah. So, the difference of an influence line diagram from a bending moment or shear force diagram is apparent. Influence line is the effect, that is the bending moment of a moving load only at a specific point, whereas the bending moment diagram itself is the variation of that effect due to the fixed loads at all points. So, this is the difference with the bending moment diagram and shear force diagram. Although the book spent a lot of time over it, and they try to tabulate the difference sometimes, making the student feel that this is a very basic quantity of interest. No, it is the present representation has changed. It could have been other way around. It is the most convenient for the practicing engineers, and that is how it is represented. Its difference needs to be understood at the outset before you actually try to venture for more topics. It has to be understood properly, but there is no point in spending more time here. It's fundamentally different. Now, influence lines are constructed. How? Now, we understood what is influence line. We understood the basic entities. Now, how to construct? We will construct. We know that it's the effect of a unit load moving on a structure. There can be two ways. One is that by tabulating values of the function, either reaction, bending moment, etc., at a specified location using static equilibrium for a moving unit load or otherwise, and the influence line equations for various segments of the structures are formed and plotted. That is two ways. One is just tabulate the values at different discrete locations, or you form the equations of variation and plot them. Both are equally useful. Most of the time we will be actually tabulating the values at critical locations and joining them with actually the lines which are suitable for statically determinate structures. We will see that they are straight lines, and we will explain to that why, and for statically indeterminate structures they are curved. So, an equation may be better, but sometimes it will be cumbersome. So, we will go for determining the values at discrete locations. The approach can be experimental as well. If you want to draw the influence line diagram, we will see that Muller-Breslau principle will give you access to draw the influence line from experimentally. So, this is the fundamentals of the influence line. I have spent quite some time. So, now I have spent quite some time, 45 minutes on this issue on the first day only. Now, we can proceed very quickly because the entities will be clear to you. I hope you understand what is shear force diagram and the bending moment diagram. You understand what is an influence line diagram. You have not drawn so far. You understand the difference between them. Also, a static indeterminacy and determinacy, the sign conventions for plotting the shear force and bending moment diagram. all these things are known to you, and then we can proceed further with examples that how to draw them for different effects. Let us draw the influence line diagram for statically determinate beams. The example 1 is the influence line for reactions. So, how do you do that? You can have an unit load moving, you can place it at an arbitrary location at a distance x. You can either form the equation. Suppose we are interested about the influence line for the reactions at either end. So, it is AY and BY is I have forgotten to put AB here in the beam, but it is here AB. So, this is a beam simply supported, this is pinned, this is roller. So, if we have a load vertically, you will have two vertical reactions. Let us see how this reaction vary as the load moves. I have designated as a section where we are interested about finding the variation, and you can have the equations of them and you can plot them. I have taken it from Professor Hivlar's book directly, and I have drawn the figures, and this is how is the variation. That means, if you are this is the influence line for AY. So, if you say that the live load is here, if your question is that this is the influence line you have drawn using the equations and also the discrete points at different, and this is the reactions at BY. As the live load moves over the span, this is the variation of the reaction here. Please remember, it is the change of the reactions here. So, if the live load is here, this is the effect of the changes into the reaction or the reaction here. If the live load is here, this is the reaction here. So, this is the use of the influence line diagram. Now, let us see what it can do. First of all, if somebody asks me which location of the single point load the reaction at A is maximum, it is immediately apparent from the diagram that actually the diagram goes positive and maximum here. So, it immediately says that yes, from the influence line diagram it is clear that the maximum is when x equal to 0, that means at the left end, correct, we know from statics. Also, suppose there is a load placed somewhere, it is required to find out the reaction, the maximum reaction at B or any place. It can be found out from the value of the quantity of that the influence line quantity multiplied by the load itself, and you can easily find out for them. Also, if it is asked that what is the reaction at A and B when a 12 kilonewton load is placed at a distance of 2.5 meter from the left end, that can also be found out. So, in a nutshell, what is there? You can find out that a reaction at A, what is the maximum value apparently from the diagram. You can also find out the maximum magnitude, and which is the corresponding location of that loading, that can be found out. This is the maximum value from that, and also you can determine at a particular location if the load sits, what is the value of the reactions else at both ends, immediately it can be found out. It may be appearing to you that there is no need for influence line diagram, I can find out from statics. Yes, this example is preliminary, explanatory to the students, that is why it is so easy. It is meant for practical bridges where the structures are complicated, the live loads are many, they have the different load paths, and you have the influence diagrams ready. So, that is how it is actually very convenient. Now, see the shear forces, I no need to explain very actually in detail, because we need to just have the statics known. I need to draw the free body diagram at a section. If the question is that what is the shear force, how it is changing when a unit load moves onto the structure. So, I can have the unit load here, I can take a section for different parts of the free bodies, solve the static problem with the sign conventions of mine, and then find out the shear forces as the unit load moves, and we will be landing up into this kind of diagrams. You see, let us take it here that I am interested about, let us say that I am just finding out the shear force at C. You know that shear force at C, when you say, you actually find out the shear force towards its left and towards its right. So, you say if it is suppose the force 1 kilonewton is just at the left, then you are sitting at C, how you look at it? You have a reaction of 0.75 due to this 1 kilonewton load, you have 0.25 reaction load onto the right. I have shown it later. So, here you have a shear force upward 0.75, downward 1. So, you have downward 0.25. According to your sign convention, when you look towards your left, when you look towards the left of the section, you have already agreed that you will have that positive. So, it says no, I have a downward force of 0.25. So, definitely according to your sign convention in the influence line diagram, you must plot that shear as negative, and as this is done. So, this is plotted as 0.25, that is why it is negative. You can see the shear force diagram and you can see the influence line for shear force at this location, and now you can digest that. So, you do the exercise. You take the beam, put the load here of 1 kilonewton, find the shear forces and draw the shear force diagram, and also you make the 1 kilonewton load moving onto the beam and draw the shear force diagrams repeatedly, to draw the influence line diagram for the shear forces, and you will immediately recognize the difference. You can readily see that here it is 0.25 on the right, you have 1. So, you have onto its right when the load is just right to the section. When the load is just right to the section, you have 1 down, 0.25 up. So, you have net 0.75 down. According to you, you have right down positive. So, you have a positive quantity in its influence line diagram. That is why you have this is up and positive. Now, I am not going to draw many more. The bending moment at C can also be drawn. So, here you can see the influence line for bending moment can be drawn similarly, and the diagrams you can draw the actually for the different load positions of the moving load. You can find out the shear and the moment here, and plot the influence line diagram for bending moment. It looks like that. You do the same exercise. You put a load at 2.5 meter distance, draw the bending moment diagram. You make that 1 kilonewton load moving onto the beam, draw the influence line diagram. If you land up into the same figure, then also you interpret what is the difference between them and what use it will be there for this diagram. And this is the values are continued. I believe this is actually the end of session. I once again, just since I have 1 or 2 minutes time, I can just explain to you about the bending moment, the drawing the shear force and the bending moment diagrams, and the influence line for shear force and bending moment. See the bending moment, how we draw here with the sign convention. Here is the shear force influence line, and here is the bending moment. You see here, if I sit here, there is a force here of 0.75 if the load is here, just here. So, it is 0.75, and then you have 1 here. So, your bending moment, if you consider here at this section, if you say this load has just passed this section, you have 0.75 into the calculation is 0.75 into 2.5 the distance. So, this is the load, this is the distance, it is 1.875 kilonewton. So, now you can see that you can find out what is the bending moment here as the unit load moves over that. Once it is here, this is the bending moment. Once it is here, the bending moment is this. Once it is here, the bending moment is this. You can see the bending moment is 0 once the load is at the extreme right or extreme left. True, the load is directly transferred to the supports. How can it bend the structure? That is all. Okay. So, now this is what is called the influence line for bending moment, and this is our end of session 1, and it is open to discussion, and we will be awaiting you for any questions you have. Before that, let me recapitulate what we learned. Apart from the basics of influence line diagram, we have learned for simple beams how to draw the influence line diagrams for reactions at supports, the shear force and bending moment at section. Thank you very much. Good morning everybody. Once again, we are starting the influence line diagram, the second hour on the first day, the session. Before we go to the actual session and its contents, let me recapitulate what we have learned in the first 1 hour. So, this is the slides. So, you can show the slides. We will show the slides. This is day 1, session 1. It is the contents, and then the introduction to influence line diagrams, how it is actually came into existence, what is the benefit of them, how to draw them, everything I have tried to explain to you. And then this introduction, yes, with an emphasis that it can be drawn experimentally. We have taken examples of a beam, we have drawn the influence line diagram for reactions, we have drawn the influence line, and also we have pointed out what is the benefit of drawing that influence line. And next is that what is the influence line for shear force, how it looks like, and also a special emphasis to you on to clear your sign convention. I will suggest you draw the shear force diagram for the load here, draw it and understand the sign conventions as well as the difference between diagrams. Next, we have drawn for the influence line diagram for bending moment at a particular sections. So, and then this is the diagram. You can understand what we mean to say is that we are sitting here onto the structure, and the load, the unit load is moving over us, and I am trying to feel how the bending moment at where I am sitting is actually changing with the locations. You can check the maximum will be here because the things will bend most, and also it will be less than 0 where it is on the supports because the load will be directly transferred to support. Another thing you might have noticed, which is that all the diagrams, the influence line diagrams so far we have drawn are actually straight lines. That will come next when we discuss the Muller-Breslau principle, but right now let us understand something else. So, this is what is the first part of our discussion of session 1. So, let us open the session 2. Let us start with the PPTs of session 2. This is day 1 session 2. So, determination of the value of a function due to the actual loading. I have given an indication how to do that, but let us now understand it formally, do that for a particular loading and clear our minds. So, once the influence line for a function, suppose reaction, mind that the reaction is an external resultant, stress resultant, you can say the reactions. We give a point load as a reaction, but it is the external stress resultant, which is sum total is the reactive, the resultant force. And also there are internal stress resultant, shear and moment has been constructed, and the position of the live loads which produce the maximum value of the function can be determined along with that maximum value of the function itself. That means you are determining two things. One is that where that function is becoming maximum, and also what is the maximum value of the function. Two types of loading, concentrated loads and uniformly distributed loads are discussed. However, the working principle of the methodology, since we have two distinct very preliminary, the first hand approach that we are either discretize the structure and finding out the values at different locations, or we are finding out an equation and determining them. So, it is equally applicable to non-uniform loads, but usually we do not discuss, it is not needed, that will come in terms of point loads. So, now before this is what we are now after. So, if we are interested about for a concentrated load F acting on a beam at a distance x from the left end, the value of the function, can be determined by multiplying the ordinate of the influence line at that location at distance x by the magnitude of the loading itself. Now, you can easily guess what is the efficacy of drawing this diagram. The diagram is ready, the ordinates can be easily determined, and of course, you can guess that this type of simple things can be easily programmed in computers. So, if such diagrams are input as computer as the variations, the functions, it can be determined very easily and quickly. For example, if it is required to find out the reaction at A of the beam shown due to the action of the concentrated load 15 kilonewton at a distance 2.5 meter from the left end A, it can be readily be computed as 0.75, because the 0.75 is the ordinate. multiplied by the load itself. So, I have to just track the influence line ordinate there, and at that location the abscissa I am defining with the position of that section, and I can easily find out the effect of that loading as 11.25 kilonewton. It appears that it should reduce from 15 to this. That means, if the load is here, readily the reaction can be determined from the influence line diagram. Next is that for any uniformly distributed load acting on the same beam, the value of the function can be determined by finding out the area under the influence line diagram for that function multiplied by the intensity of the uniformly distributed load. This is also apparent for us. I can say that the uniformly distributed load is basically consisting of point loads at different locations. So, let us assume that there are point loads everywhere, they are going down. I have learned how to deal with the point loads just before this. So, why not I can extend the point load concept to here? Yes, I can, and the infinitesimal or this length, suppose the length dx, it will lead into through integration through the sum total effect of the uniformly distributed load or any varying load. Basically, it is the integration. So, I am not really restricted to uniformly variation load. I can find out from other loadings as well, since it is differential element. And you can find out by integration the effect is df is equal to omega 0 into dx for this elemental loading, and for the total loading it is df is equal to omega 0 y dx is equal to this. Now, you can say that omega 0 has already come out of the integral because it is uniformly distributed load, but if the load is not uniformly distributed, it will be a function of x if I can express, or segment wise also I can express for different through different integrals. If I totally fail, I will have the summation at different ranges, no problem. Anyway, the df is this is the it appears I have in my PPT there is a there should be a correction. I have directly loaded actually for df. In fact, it should be for the f. In fact, please correct it. It should be for the f, not df. So, df is this. So, previous slide. So, I will correct it when I know. So, df is this omega 0 dx. When you are finding out for f, so the d should not be there in typing. It is a typographical mistake, and it is this integration, and it is the area y dx is nothing but the area under the influence line diagram, and it gives 10 kilonewton. So, effect, if you see the previous problem, sorry, this is, if you see the previous problem, it is 2 kilonewton per meter, it is 10 meter, you can well guess the total load is 10 into 2, 20 kilonewton. So, the half load both sides, it is 10 kilonewton each. So, you know the answer, that what is the effect at RA, maximum effect at RA, you already know the answer. So, now if it is the total load, it is sum total of that load, it has come like this through the influence line diagram. It convinces and it proves, and it also gives us confidence that what we did is correct, and I am going to extend it further to complicated problems, that I am going to find out for the distributed load, uniformly distributed load, the area under the influence line diagram and multiplied by the uniformly distributed load and determine the effect. If this load is varying, I will retain it inside the integral and I will express it as a function as I have expressed this y, and then I will just do that. So, now the thing is that once again previous slide, yeah, you may see that UDL is spanning over the entire length of the beam. There is a difference in some problems, technically it is same, but still there is a difference in detail. If that omega 0 is occupying the length shorter, there is a spelling mistake also, it is a shorter than the span, the effect on the reaction can be found out easily by determining the area under the curve between the points of occupancy. So, you understand that we can have the quantities determined this way, and next is the so that's it for right now. Let me recapitulate quickly that what we have discussed in day 1 session 2, that we are the influence line diagram once it is drawn. So, either with the concentrated load or with the uniformly distributed load, how you actually deal with to determine the actually the quantities. So, for the concentrated load, it is the ordinate of the influence line diagram, which will be multiplied by the load itself to determine the net effect. So, it is 15 multiplied by 0.75, which is the ordinate here, it will be 11.25, that is the reaction here when the 15 kilonewton load is here. Please once again see that this influence line diagram, it is once the load is here, I am always sitting here. So, 15 kilonewton load, when it is here, I will face the full 15 kilonewton load on me, and I will say that the reaction is 15. That will come. You may say that this is plain statics, it is on the support. So, I know. Now, how to find out from influence line diagram? The influence line diagram is 1. So, it is 1 multiplied by 15 here. The load is here, it is 15 into 0.25, because the value is suppose 2.5 meter from the right end, it will be 15 into 0.25, that means 1/4 of 15, or it is 7.5 divided by 2. So, 3.75 will be the actually the answer. So, 7.5 divided by 2, it is that 3.75 is the answer. Now, immediately for it can be extended, it has been extended to the actually the uniformly distributed load. Now, from point to point, if there is a uniformly distributed load, in this example I have shown you, it is extending from this end to this end. That is why we have integrated it throughout the length, area under the influence line diagram throughout the length. If it is less, if the occupancy of the uniformly distributed load is less, you have no problem. You will find the area under that portion. Suppose the load is from the right end to here, then you will integrate and find out the area of this triangular portion of the influence line diagram multiplied by the omega, which is the uniformly distributed load. Okay. So, I think that is it. So, we will come back to this application of this later. So, let me go very slowly. Now our before we have planned for today only this Murrell-Breslau principle. We have planned less for day 1, because the principles and the fundamentals are to be understood very clearly, without ambiguity and with perfectness. Please be with us. We are not rushing to finish a syllabus. The syllabus can be finished from the book, no problem. What I am going to discuss is the Muller-Breslau principle, and it was the you can say it is 1886. Many of our principles are well actually discovered century more than 100 years ago, and that is why you can say that this is very well established principle. So, Heinrich Muller-Breslau developed in 1886 a methodology for rapidly constructing the shape of an influence line in a qualitative manner. The principle known as the Muller-Breslau principle stated for a beam structure, if we state first let us have the statement, then we will discuss what does it mean, then we will discuss whether from our perception we can feel that, we need to feel the structures, otherwise it will be difficult in future. So, the influence line for a function, reaction, shear or moment is to the same scale as the deflected shape of the beam when the beam is acted upon by that function, Okay. Thus, the capacity of the beam to resist the applied function must be removed temporarily to observe the deflection of the beam when the function is applied. You please go through once again, let me display this page for a couple of minutes. What it says that, okay, well, you want the influence line for the reactions, fine. First of all, deactivate the reactions. That means the beam reaction at the left end, suppose I am interested about the influence line diagram of the reaction at the left end. Let me destroy it temporarily. Let me destroy it temporarily. So, how the beam looks like? It will be trying to actually fall down from that, or if I just fall down from that. Now, while it is falling down at that end, let me prop it with the reaction. Let me prop it with the same reaction I have removed and see that what shapes it takes. That is the influence line diagram for the reaction itself. It looks ridiculous that what is the relationship between them. So, that is the Muller-Breslow principle. With the principle of virtual work, you can prove that. I am not going to that proof of this, because the theorem proving it will not convince the students the powerfulness of the let us apply that to structures and see that how they are used, and then the student will be actually convinced that it works. Let me read carefully once again the principle. The influence line for a function, reaction, shear or moment is to the same scale as the deflected shape of the beam when the beam is acted upon that by that function. By is missing here, just put it. Thus, the capacity of the beam to resist the applied function must be removed temporarily to observe the deflection of the beam when the function is applied. Two steps. I need to destroy its resistance against that function, and then again put back the function there, and then observe what shapes it is taking, and that is my influence line diagram qualitatively to some scale. So, that what probably I am missing, if I put a unit load, I will be able to accurately determine what is the reaction due to that unit load in numerical quantitatively, but that is not possible. The shape will give a ratio of deflections and ratio at deformations at different parts of the beam, and that might be I need to bear with. So, I lost the quantitativeness, but I may gain better insight into the behavior of the structures for the influence line. Next is that, let us take an example. Example 1 is that influence line for reaction of a statically determinate beam. You see, a beam is there, AB. So, I am actually applying the thing is that I am applying no, just before that its influence line diagram. I have a unit load which should move on that. That is my traditional definition, but Muller-Breslow law principle have not talked about my unit load. Rather, it has told, what do you want, tell me. I want the influence line diagram for the reaction at A. The first is that I need to destroy that. I need to remove the capability of the beam to resist the reaction at A, that but not any other stress resultant restraint. That means, the beam will be only allowed to slide down or up and nothing else. Okay, I allowed. Now, the same AY, I bring it back and see how the beam is deforming. Now, see, one thing you must remember, that this is a linear analysis, as a superposition principle is valid. That is why all displacements are small. So, even if my beam length is this, it goes up, means now this is my beam length. In fact, if you draw, it will be a circular arc. We neglect that. We say that this is the new configuration. You have to be accepting this in the true sense when the deformations are very small. Suppose a few meters span of beam, how much it deforms in terms of millimeter? It's even fraction of millimeter sometimes. So, if you say that the delta by L ratio is very small, and with that the difference between an arc and difference between this straight line is negligible so far as any practical analysis is concerned, and that is how I am drawing the deformed shape of the beam like this. Now, can you not find out the similarity of the influence line diagram for RA, which you have drawn earlier with the unit load moving? Yes, it looks like that. So, it looks like that. Only thing missing here is that I do not have any idea about what is this length should be for finding out the quantities elsewhere. That means, I cannot use it directly in terms of finding the quantities, because it is not based on the unit load concept, but definitely it gives me a very accurate description of the shape of the influence line, and once I know it, I can do it very easily. Now, this is what is the fundamentals of drawing the qualitative shape of the influence line diagram using the Muller-Breslau principle. So, now this is now is to be tested with. So, this is the influence line for, actually it is A y. So, it is the y direction is this, A is this left point. So, it is A y basically, it is not R y. So, this is what is that. Now, if I put 1 here normalization, then all the ratios are actually maintained accurately. Now, let us come to another influence line for shear at a point of a statically determinate beam. So, now if I have to draw the influence line diagram for the shear, what you do, can you remember that you have an unit load which are actually moving onto this the beam, and you are trying to determine that what is the shear at that particular point. So, it is the influence line diagram for shear at a point. You need to define the point where you are interested to determine the shear. So, let us see that I am interested about to determine the shear at C when a unit load moves here. That is my influence line diagram quantitatively, that we have done earlier and probably we have learned correctly. Now, if I have to follow Muller-Breslau principle, already I have applied this Muller-Breslau principle to the reaction of a beam, which was somewhat easier, in terms of sign convention as well as in terms of understanding of the movement of the structural parts, which will be when acted upon by the forces, how it displaces. It was much easier with the actually the reactions. Now, it is to be tested with the shear. So, influence line for the shear at C of the beam, similar to the previous example, is obtained by temporarily removing the shear resistance, and the beam deflects in a manner consisting of 2 rigid bodies, giving the qualitative influence line diagram. Now, here there is a catch. You must understand it properly, that what you are exactly doing, there is a source of confusion for the students here. Clear it once for all with your sign convention, which is accepted by all of us, that for the shear, if you take a section for the shear, left up right down is positive shear for us. With that concept, if I say that I have temporarily removed or temporarily destroyed the capability of the beam to resist shear, then what will happen to the beam if the load is applied? If the unit load is applied, then this part is going down and relatively this part is going up. So, now you can say that I understood that the shear capability of the beam is gone. So, it is going to be sheared up there, but how can you determine which part will come down and which part will go up? For that, you need to clearly understand your sign convention, and here the books can differ in the look of the influence line diagrams drawn. Do not be concerned with that. Learn from a single book if you are confused, as I told you, or clear your mind right now. So, now here if you say this is one rigid part and this is one rigid part, once the shear resisting capability between them has been destroyed, and if you consider this particular rigid part, once again see your convention, you already told that it is left up right down is positive. Definitely this shear force is making this part down, that is why to me this VC, which is a shear force at C, is positive according to my idea. Next is that this part is also, this V is also pushing the left part up according to my sign convention, left up and right down. It's left for this portion and right for this portion. Is this is actually a positive sign convention for me. That is why we have drawn, and with that this goes down and this goes up, and that's the actually the positive shear here and the influence line diagram and the negative shear influence line diagram. We will see more of it when we actually find out the values of the positive and negative shear at different locations, and we will understand what is happening. So, now this is what the Muller-Breslau principle can actually offer to you while drawing the influence line diagram for the different structures. So, now this should be concluded. In fact, we will see the section for the truss and show them. Now, let us come to the influence line diagram for the bending moment, because so now this is what is there, the influence line diagram for the bending moment at a point of a statically determinate beam. Here once again carefully observe, clear your mind. You have done for the reaction, applied the Muller-Breslau principle, destroyed the capability of resisting reactions. You have done for shear, you have destroyed the capability of the shear resistance at a section. Now, you are going to draw actually the qualitative shape of the influence line for bending moment at a section. What you need to do is that we need to destroy the bending moment resisting capability at C for the beam AB. How can you do that? You can do that with an internal hinge developed there. Internal hinges, you know that you might have seen that internal hinges when you suppose you are traveling by a ship. So, you get down at the jetty. So, one platform is projected from the ship, and from there something is hinged and that is touching the ground or the jetty. So, even if the ship actually rolls and it has a pitching motion or something, it goes up and down, then due to the internal hinge the system does not develop any stresses. So, it is a very nice way to release the stresses, one of the stress resultants. So, only due to the resistance the stress resultants will develop. So, if that is destroyed, but the other stress resultants are well kept. So, we have developed an internal hinge to the beam. Now, it has to be now acted upon by the very stress resultants for which we are searching the qualitative influence line diagram. So, we are after drawing the qualitative influence line diagram for bending moment. I have destroyed the bending moment. Now, I have to apply the bending moments there at the section. So, there what I apply is like this, so that this part of the rigid body is having a sagging moment if it is resisting. In fact, it is a rigid body. So, rigid body cannot bend, it will just move, it will rotate due to the moment, it will move due to the force. So, it will try to actually just rotate as a rigid body here, and here again it will be like a tendency, it is a tendency of the sagging moment, although it is a rigid body. So, it will not bend, but I have to follow a certain sign convention. So, this is the convention of the sign, that this moment is I am drawing it as my positive, and let me go ahead and see that what is coming there due to that condition. Now, if I do that, this rigid part will go up, and if I do that, this right rigid part will go up, and if I still say this is a linear structure and there is not much difference between this length and this length and this length and this length, I can still say that this shape is actually replicating the qualitative shape of the influence line diagram for bending moment at C. So, this should be enough convincing to you that the influence line diagram for the bending moment is influence line diagram for the bending moments actually works. So, I have kept the presentation bare minimum. So, this is the end of session, but I will extend this idea to some of the structures where I can explain to you. So, let me let me explain. So, by this time my colleague our research scholar assistant actually opens that. I will show you that how it works for some of the structures very well. So, suppose let me concentrate on this particular this thing, your one I can draw it here, and I can say that this works for the truss type of structures as well. Okay. So, now this example I will show you once again also. Now, let me see, suppose there is a truss, we will see that I have not discussed about how to draw the influence line diagram for the truss. Since I want to extend quickly this idea of Muller-Breslau principle to other structures, I am trying to prove that this works for this kind of structures as well. We have the influence line diagrams are for the stress resultants. It works for the reactions which is external, it works for the internal which is the bending moment, it works for the shear forces. So, it works for the axial forces also. So, if I am interested to plot if a unit load moves on a structure which is a bridge, I will come to that later. Let us now only discuss that Muller-Breslau principle as it applicable to other structures. I can only say that let me examine carefully that right now. Okay, let me draw the structure which is given later in example, not the other one, because then the people may be confused. Let me change this figure to this. So, what is there in the yeah. So, this member. Okay. This is a statically determined structure, unit load move. Now, you see, if I am interested about the drawing the influence line diagram for the axial force here, what should I do? According to Muller-Breslau, I should reduce it to I should destroy the capability of the resistance for the same stress resultants of the structure. If I am interested about the influence line diagram for the axial forces, then I should destroy it here first. So, I have destroyed. So, now it is a cut. Now, if I try to bring it together, and if I have an overlap of length. So, I am applying that, suppose I am applying the same force which was there as a member force here, and if I have an overlap, then what will happen to this structure if this is actually have a your pin support, and if this is a roller support, I have destroyed it here. All joints are pin structures, and then if I am concerned with this structure, then this will try to if I am just putting them together, if I am putting that together, then this will go up, is not it? So, this will go up, this portion will go up, and this will be like this. So, this will be shortened, this length of the truss will be shortened. Let me draw with an overlap. So, the portion which was a nice rectangle or a square, it will now become rhombic. If it becomes rhombic, and then I can say that if it becomes rhombic, it has to actually be deformed. So, this portion will go up. My drawing is not proper, I am showing you my original drawing which I have given to you. You can see this particular, I am explaining Muller-Breslau principle to the students. So, it is that I am interested about this member force, what is happening when a unit load moves onto the bottom chord. So, I have destroyed its capability to resist tensile forces as I have shown here, and then I have then let me show the deformed configuration. These two portions are coming together, and this will be lengthened, and the truss will be looking like this. So, there is a tendency of this line of joining these nodes to have the shape of something like this. So, when you study in the next chapter, so it is too early to actually extend the ideas of the Muller-Breslau principle because it is we need to wait for drawing the traditional way, the influence line diagram for the truss, but I say that the Muller-Breslau law principle works for the truss as well, and it is very quick. This proposition is very quick, and even it is possible experimentally as well to have a cut and just pull it, and you will have the shape of the structure exactly showing the Muller-Breslau law principle. So, let us now recapitulate for this session. This is I have taken extreme time for these two sessions, just because this one is that correctly understanding what is happening when we draw the influence line diagram, that is to be understood perfectly, and it is to be understood how the effect of a concentrated load are taken into account. So, it is the load multiplied by this particular influence line ordinate which will give that effect there, not anywhere else. And also we have iterated that for uniformly distributed load, it is the area of the influence line diagram which will be useful. If in case the load actually is not distributed fully, but if it is distributed partially, then also your influence line diagram which you have drawn, which was this for R A. So, this is A B. So, if it is R A, then what you need to do? You need to concentrate on this part of the area of the influence line diagram multiplied by omega. So, is the area of this trapezoidal portion along with the omega, which will give the net effect for this smaller load. And next is that let us see that the integration works. A caution, none of the books discuss about how it is when it is non-uniform, what will be. Nothing, you just integrate it within the express as a function and integrate it, no problem, you will find the effect. And another most powerful method in one of the very powerful method in mechanics and most powerful method while drawing influence line diagram is the Muller-Breslau law principle. It is to be understood today itself for going to the next 3 sessions successfully. So, it is the principle states that the influence line for a function is to the same scale as the deflected shape of the beam when the beam is acted upon by that function. Thus, the capacity of the beam to resist the applied function must be removed temporarily to observe the deflection of the beam when the function is applied. I have repeatedly stated just for that when we go for the next session tomorrow and day after tomorrow, we will be a little bit faster and showing the results. You need to interpret them quickly in terms of quantity, quality and sign convention. There should not be any confusion with the sign convention. So, you released the beam for the reaction, applied the reaction and seen how it deflects the rigid body. This is the influence line for reaction. This is the, you see, you released it here for shear, but not for moment, If you actually go like this, it will be subjected to moment. Now, this is the shape it took, and that is the influence line you have drawn earlier. Sorry, this is for shear, and this is for bending moment. You destroyed the bending moment capability by incorporating internal hinge, and then you applied the same moment with proper sign convention. You got the shape. That is the influence line in qualitative terms. So, these are to be understood properly. This Muller-Breslau law principle gives qualitative shape. So, for the quantity should come from the actual analysis. You know the shape, so the ratios are clear. You find out the value at a point, you just scale it down to all other points, and then you will get the quantitative, qualitative both as well. So, like that the influence line diagrams will be drawn, and we can apply to truss type of structures. We will see that we can apply to building type of structures. In our the class note, the last session, we will touch upon that. We will see that we can actually, I have not prepared the notes or for you for the warehouses and the other the girders, the frame, the floor girders. There is something more to say that we will say when it comes to our structure. So, can we have the session? Yes. So, let us open the session for discussion and stop our traditional talking. So, we have any question? Can you explain again how to calculate area under the influence line diagram? Can I just, hello, the question is how can we, yes, area under the influence line diagram has nothing special with influence line. It is the area under the curve. So, you use the calculus or geometry whatever you want. So, you can, as I explained, that your differential element you take and then just find out the area of that and extend it from one limit to the other. So, it is a limit in integration which will define the area under the curve, or sometimes if the figure is very regular, if you are familiar with them from the school geometry, you will find geometrically the area. It is very simple. It is very simple. Try that. Thank you. And next question. Yes, there was a question, how to draw the influence line diagram for uniformly varying load. Probably your question is how to draw the influence line diagram for uniformly varying load. Yes, we will come to that. We will come to that influence line diagram. So, the thing is that you are probably confusing you are not going to draw the influence line diagram for uniformly distributed load. You are going to find out the effect of the uniformly distributed load due to the effect of the uniformly distributed load using the same diagram which is drawn due to a unit load. So, the area under the curve accounts for the uniformly distributed load. So, there is no separate diagram for separate loading. Probably this was the confusion. You are drawing the influence line diagram for a unit load and finishing it, that is it. You have the influence line diagram ready for concentrated load, multiply by the ordinate. For the uniformly distributed load, find out the area multiplied by the intensity of the load. For non-uniformly distributed load, suppose triangular or irregularly varying, I have not discussed because not to confuse right now. You also keep it pending for your future learning, but there is no problem that is to be incorporated within the integral. So, the integral term, either geometrically you express the figure, in terms of the elemental variation of the load, or you use the geometry to have the combined variation of the intensity with the geometric length, and then integrate it simply, no problem. So, it is overall integration. For uniformly distributed load, your omega 0 comes out of the integral. So, you are left out with the geometric entity of finding out the area of under the curve. So, area under the curve is very simple. So, that is you can integrate with an elemental area, or you can use the geometry. Any other, can you please, you can also confirm if the lecture was okay. I have delivered it very slowly, repeatedly, and because we have discussed two fundamental principles. One is with statics principle, one by one all the loads, and also the Muller-Breslau principle, which is actually qualitative. Both the principles are our tools for further progress. So, I have been very slow there. Tomorrow the two sessions will be a little bit faster, but I hope if you understand these two sessions, you will understand all of them without any difficulty. Let me summarize both the sessions. Fix up your sign convention, what you want to do with the bending moment and the shear forces. If in confusion, stick to a single textbook for time being. They will follow only one convention, and go ahead with understanding the topics of the influence line, be it drawn this side or that side, or this positive or that positive, it will not matter ultimately. The answers will be same, everything same, and clear your mind about the difference between a shear force and bending moment diagram and influence line diagram. I am telling you it is not easy. The bending moment diagram, shear force diagram is very natural and spatial, the distribution is spatial. We can feel them. To shift our mind from that feeling to a feeling of I am sitting at a place and something is moving over me, and I am trying to find out the effect at the same place when the load is moving, is actually difficult, and a shift in mind is required. Do that. Always think about the influence line is the effect at a point. There are a lot of details in the textbooks, as I told, but everything will be clear once you understood this. This much detail is just it is giving you assurance when you solve problems, either in your professional career or as a student preparing for exams, or even enriching your knowledge when you get more time, free time. At that time it will be very helpful, but fundamentals are very few. The textbooks which can keep only the fundamentals very concise, they are most appropriate textbook. I have seen one more textbook I have not shown here. It's Alexander Chajes, and I will show you sometime next that the books in our library, one copy is there, is very concise in all respects, and it is very useful. You do not have to worry about the materials. We have lot many sessions of influence line in our NPTEL course. See the online course, everything I have discussed, everything are there. You will be very much useful. This will be very much useful when you see in detail. All I have told, everything is there in our NPTEL course. Everything is there in the textbook. So, do not worry, there are 4 modules of the these things. Yeah, 4 modules of this this NPTEL courses, and also the textbooks. Thank you very much. Bye. See you tomorrow.